Ross. I'm a researcher at IBM, and I'll give a talk that's in 4 parts: an introduction to quantum error correction. The first part I'll talk about the devices and give you an idea of how they work. In the second part I'll talk about how we measure the error of the whole system using this concept called quantum volume. And then in the third part it'll be much more like a tutorial. I'm going to go through the main ideas of quantum error correction using examples from QuizKit, and you can follow along if you'd like. You can construct some of these circuits. You can run them in the simulator. I'll show you how to do that. And in the final part, I'm going to step back from that and give you a picture of how we might do large-scale error correction, in the much longer term. So why don't I get started? What we've been talking about so far is the idealized quantum circuit model. So this is a block sphere. The pure states of a qubit, they live on the surface of that sphere, right? The distribution of amplitudes between the 0 and 1 state, theta, that tells you the latitude here, and this phase phi, that tells you where you are on the equator, right? And so we have a collection of these qubits, and they're in some pure state. This is described by 2 to the n complex amplitudes. And then we apply from left to right a sequence of gates. And we can take whatever unitary operation we want to apply and write it down as a sequence of 1 and 2 qubit operations. We can always do that. And transform our input state to some final state, which we then measure. And when we measure that, we read out a particular bit string B with probability that corresponds to the amplitude absolute value squared. Right, so the goal of quantum computing is to implement, build a device that realizes this ideal circuit model, where each of these operations is highly reliable, and it behaves more or less exactly like this mathematical model. But in reality, we're implementing these with real physical devices, and they're not ideal. And so I'm going to review these devices and give you an idea of how they work. So at IBM, we use qubits that are based on a device called the transmon. This was pioneered by the Sholkoff group at Yale. And our devices are fixed frequency Josephson junction qubits. Fixed frequency means that the parameters of the device are determined when you fabricate the device, and then they're fixed. So in this case, the frequency omega of the qubit transition is fixed, and this other parameter called the anharmonicity, which I'll explain. So the picture on the left is one of these devices, and just to show you the main components, there's this is a big capacitor, and this line in the middle that you can't quite see has in the center of it something called a Josephson junction, which acts like a nonlinear inductor. So together, right, if you had a normal capacitor inductor, you'd have a resonator, and this would have some equally spaced energy levels. Now that's difficult to control, because if you wanted to drive transitions here, you would also drive transitions here, and so on. So you need to somehow be able to address the qubit space. The way they do that is by, this Josephson junction adds nonlinearity, and the shape of this well changes, and now the energy levels are not equally spaced anymore. And you can address this one, 0, 1, which is the qubit subspace. This is an approximation to the Hamiltonian of the system. There's the oscillator, the harmonic oscillator part, and there's the anharmonicity part, this shape. Typical parameters like microwave frequencies and anharmonicities are, around here. So these devices are, these transmon devices are arranged in a plane. Here are 4 of them. And each of them is coupled to its control by a resonator. So you can see, they're color-coded. That resonator is used to drive single qubit gates and to do measurements. And then the qubits, the transmons, are coupled to each other by resonators as well, which we refer to as bus resonators. Their frequency is somewhat higher. They're coplanar waveguides in this picture. So, you can, over the last, say, this is 5 or 6 years, this is an example of some of the devices that have been made at IBM. These have been all used to do research that's published in a variety of papers, looking at everything from 2 qubit operations to parity check operations on 4 and 8 qubit devices. variational quantum eigensolver algorithms on 7-qubit devices, and most recently the IBM QExperience devices. Here are the 5 and 16-qubit devices. And the 5-qubit device was used to demonstrate an error detecting code a couple years ago, shortly after the demonstration of the same code in ion traps. Okay, so this gives you an idea of sort of the progression, where we are today is somewhat beyond this device. You've heard there are commercial 20 and 50-qubit devices. All right, so let me explain how the gates work. Maybe this is review, but I'll talk through it. All right, so the main operations we have are 1 and 2 qubit gates. The single qubit gates, the goal is to implement an arbitrary rotation on the block sphere, an arbitrary unitary. And we can decompose that as Z rotations sandwiching a Y rotation in the middle. Okay, and this is good because, well, these Z rotations can be done essentially for free by changing the phase of the carrier. So they sort of, for the kind of scale of error that we're talking about, they're instantaneous, they're free, they have no error. But then this RY gate we can implement by calibrating just a single pulse, a pi over 2 X rotation. And by alternating these X rotations with these Z operations, we can implement any single qubit operation. And the costs are very similar. So there are the free Z rotations. There's a single pulse U2 gate, which is a subset of the operations. And then there's any single qubit gate, which can be done with 2 of these pulses. All right. And then we need 2 qubit gates. And these are constrained to interact along the edges that are, between qubits that are coupled by bus resonators. So you've seen this picture before. This is the coupling graph for the 5-qubit quantum experience device. This may be one from a revision or 2 ago, but the ideas are still the same. You have qubits, they're coupled directionally. There's a control qubit and a target qubit at the head and tail of the arrow. And the gate that we apply in the quantum experience device uses what's called the cross-resonance effect, where you drive the control qubit at the target qubit's frequency. And one way to implement this gate is to, so this gate does an interaction that gives you a gate that's equivalent to C0 up to single qubit rotations. And so those single qubit rotations are applied in here, and we have frame changes. And the gate itself is broken up into 2 pulses, and the reason for that is that we can apply pulses in the middle to cancel some of the error terms that naturally arise. All right, so those are the 2 qubit gates. And now, of course, nothing that we apply is ideal, and there are many sources of noise. Fundamentally, what we need to do is we need to be able to apply fast, high-fidelity control and readout. So, when we don't do this, we may have inaccurate operations. This leads to error, leads to maybe systematic terms in our control Hamiltonians that we don't want to be there. And at the same time that we're trying to achieve this control and we have these channels to the device for applying the operations, we need to keep the system isolated from the environment. So, we both have knobs to manipulate the system, and there are ways that the environment is attempting to interact with it, right? So we have these inaccurate control fields. It could be other stray fields coupling in. There could be crosstalk, unwanted coupling, and coupling to the environment. Whatever it is, the materials in the device. Another way of thinking about these errors, say for example decoherence, is that you can kind of think of it as each of your qubits here is coupling to the environment, and the environment is learning something about the system, about the logical state of those qubits. And as it learns this information, it disturbs the system, which leads to errors. I'll give a much more concrete example of this later to illustrate this. All right, so this is a menu of some of the types of errors that can occur in these systems, and many of these are rather general. They would occur in a lot of quantum computing systems. So there are errors that are in this decoherence kind of category. The decoherence or damping errors, which push the qubits from their excited state toward the ground state along with some characteristic time scale. in the quantum experience devices is like 50 microseconds, but it can vary from device to device and system to system. Dephasing tends to, it erases phase information, pushes all the states toward this line. And the time scales for that are comparable to T1. I think what Ali showed earlier there, T2 overall is a little bit shorter than T1 in our systems. There are also systematic errors in the operations themselves. For example, you might want to rotate about a particular axis, but when you apply the pulse, the axis is actually misaligned. So you can have errors like this. You can also apply the pulse for the wrong amount of time, so you can rotate past where you intended to go, and things like this. Now, there are analogous behaviors that happen in multi-qubit gates as well that are more complicated. In our system, the error rates for single qubit gates that range from 0.1% to 1%. The 2 qubit gates currently they range from like 1% to 5%, and as you've seen, they vary from qubit to qubit. There are also systematic errors in the state preparation, and for example, you could just wait for a while and allow the system to relax to the ground state. But even then, there's some, there's some mechanism that's heating the qubit a bit. And so you can end up with a state that's not quite 0, but it's displaced a little bit along this line. So these errors can be, something like 1%. And it really depends on, details of this. Another thing that we've seen in Ali's talk is that there can be assignment errors in the measurement. So you read out a qubit, you get an outcome, say 1, but it's actually opposite. Okay, so that occurs, in these devices, error rates like 1 to 7%. So rather large measurement assignment errors. Now there are other types of errors that haven't come up so much, but they're there. And you will see them if you look in detail. If you design experiments to probe for these, you'll see these. So, well, all right, maybe not these, but you'll definitely see these. So I'll talk about this first. So, some things that can happen. There are these resonators that are coupled to the qubit. They also have a state. They can become excited. Okay. There are other dynamics, like dynamics of the environment, that could matter. For example, you see that T1 fluctuates with time. And there could be leakage. These the transmons are not really qubits. They have higher levels, and so operations you apply, like two qubit gates in particular, can drive the system up into the excited states. There are also multi-qubit systematic errors, and I think these are among this and measurement assignment are among the kind of dominant systematic errors in the system. There are a bunch of details here, but I'll boil it down to 2 types. First, the qubits are always coupled. So pairs of qubits that share a bus resonator are always weakly interacting. So that leads to what we call, an always-on ZZ term. It's just always there. There are also driven interactions that happen. You apply 2 qubit gates somewhere, and there's another interaction that's activated by that. In addition to that, you have cases where you drive a particular qubit, and there are single qubit systematic errors on the qubits that are coupled to it. Okay? So this gives you an idea of some, but not all, of the realistic errors in multi-qubit systems. All right, so each of these ways of measuring the error, these come from things like randomized benchmarking, and you're looking at a particular gate in isolation. When you have a whole system, it's important to characterize that, to validate that system in whole. So to do that, we've introduced this metric that's we refer to as quantum volume, and it's really sort of it's meant to capture what is the largest circuit that you can reasonably run and succeed. In particular, it's the largest square-shaped circuit, so width and depth are equal. And we want to also capture some idea of the connectivity of the device in this metric. So we look at circuits that we call model circuits. These are idealized random circuits where in each layer you apply 2 qubit gates between random pairs of qubits. And you're applying random 2 qubit gates each time. So in this example, I pick 3 random 2 qubit gates, and I partition the qubits into control and target, and I apply them. Then I choose a different partition of qubits. That's what this permutation is. I scramble the wires. I do it again and again and again. Okay. Now, this model circuit probably doesn't run on the device that you have, so you have to compile it. Okay, so we compile it to the device, and if you have higher connectivity, that will help you. If you have a variety of 2-qubit interactions you can use to simplify your 2-qubit gates, that'll help you. Obviously low crosstalk, high parallelism, and being clever in the way that you map this will all help. So you play that game, you take this, you map it to the device, and you want to evaluate how well you can run. Do you succeed or not in this task? Well, what is the task? Okay, so we're going to use ideas from Aronson and Chen. There's a problem they define there called heavy output generation. And we like to use that as a way of validating these model circuits. Because they're random circuits, we expect with high probability that we expect the distribution to have a particular shape. Okay? We also, in the near term, expect to be able to simulate these circuits so we can compute that ideal distribution view. And then we run the experiment and we see some different distribution, right? Some of the outputs we observe are called heavy. And what that means is if you take the probabilities of each outcome and you sort them, you have the most likely strings and the least likely strings. And there's some median probability that you see. All the strings that occur with probability above that median you call heavy. Okay? So that's this set of heavy outputs. And then what you're doing really is you run the circuit, you sample, and you say, is this output heavy or not? And you estimate the probability that you see a heavy output from a particular random circuit. Sorry, let me go the other way. So then what we do is we want to generate many random instances of model circuits, map them to the device, and look at whether or not the output is heavy. And we succeed if this heavy output probability exceeds 2/3 with high confidence. It will say we successfully ran a model circuit of width m and depth m if we see heavy outputs 2/3 of the time over random instances of this. Now, perfect hardware would generate heavy outputs most of the time. Okay, noisy hardware will not. So what we do is we increase the depth, and we look at this heavy output, and at some point we reach some depth where we fail this test. Okay, and then we look at, so our volume is defined in terms of. All right, this requires a little bit of motivation, right? So if we have very few qubits, we could run extremely deep circuits. And so our circuit area could be very high, right? Our quantum volume could be very high. But that's not exactly fair because I shouldn't count that as the best that my device can do, because it could be now that if I increase the width of the circuit, these systematic errors that I've talked about begin to come into play. And actually, I can't run circuits that are very deep at all. So what we want to know is, in a sense that you're using all of these m qubits fully, so that meaning, I'm applying a random circuit of depth n on them, what's the largest size circuit I can actually run? That's what this captures. So the other reason to do this minimization, say, I'm only going to give you credit if you use a lot of qubits and a deep circuit, is because there are regimes where I can efficiently simulate this if the depth is very small, or there are other scenarios as well. So we define this so that it loosely coincides with the complexity of simulating this circuit, so that we think that what we're doing is getting harder and harder. Okay. So let me skip over this. Let me just show you an example of what happens. So pick a random model circuit, use the default mapping algorithm in Qiskit, and pick a 4-qubit subset of the 5-qubit quantum experience device. Okay, you run it, you see some sample outputs. The ideal probability distribution is the empty box, right? And what you observe is the solid line in the histogram. Okay, and so any outcome whose probability exceeds this red line is heavy. Okay, and so we just sum up the probability mass of all the bars that are above this line, and the heavy output probability here is around 80%. Okay, which would be counted as a success. We've successfully run a depth 1 model circuit on 4 qubits. Okay, but you can see that as you increase the depth, now this distribution starts to flatten out. Right, here's the ideal. It's got this big peak here, but the actual circuit has a nearly flat output distribution. And now the probability has been distributed in such a way that the chance of seeing a heavy string is now just about a half. So we definitely failed to run a depth 4 model circuit on 4 qubits in this case, on this device. All right. So now here's some results. These are all in this paper, but I'll review them really quickly. Here, this is the heavy output probability for 3 different cases: simulation ideally, simulation with noise, and the experiment. And along this axis is the width and depth. So width and depth are equal of the model circuit. All right, and so you can see. Let's just look at the blue dots, right? These are the experimental outcomes. So we successfully ran a 2x2 model circuit, and we successfully ran a 3x3 model circuit. And just to be very sure, we ran it with enough shots that we could separate it from this line by 2 sigma. Okay, so we successfully ran here. And then over here, we can't run this, we can't succeed at this task for a depth 4 circuit. Okay, so we would declare that the volume is 8 here, right? It's effectively, we've used 3 qubits. Okay. The other thing you can notice is that when we compare this to noisy simulations using the qubit by qubit noise rates, the behavior is worse. And you might, I think there's more work to do to pin down exactly why this is happening, but the conjecture is that this is due to a combination of correlated readout errors and correlated 2-qubit errors, right? These are the systematic errors I was talking about. There are more details over here, but maybe I won't go through them right now. These results come from one of the 20-qubit devices. All right. So what do we expect to happen as error rates continue to decrease? Now I'm going to show you some simulations at these lower error rates. So here's 1 over the error rate. Right, so as the error is going down, we're moving to the right on this plot. And this is the log of the volume, so it's sort of the number of effective qubits, the width and depth of the circuit that we can run. What's plotted here is a couple different examples. There's a loop, there's a grid, and there's all-to-all connectivity, because the geometry matters. And you can see that it matters, somewhat, maybe not so much for the loop and the grid for these small examples, but having all-to-all connectivity helps. It gives you a greater volume. But what I want to point out is that as the error rates decrease, right, the volume increases. And when you get to error rates of 10 to the minus 3, where really your errors are kind of independent, they're behaving according to this noise model, you expect the volume to go up to, say, around the log volume to be about 15 effective qubits. So 15 by 15 model circuit at 10 to the minus 3 error rate. And this would be incredible. And it's really important to move in this direction of lower error rates and then verify that you have the behavior you expect across the whole system, say using something like the quantum volume. And you can see that the increased volume coincides with reduced error rates. Okay, but now, so suppose we continue this trend of increasing the volume over a period of time. Eventually we reach these relatively low error rates of 10 to the minus 3. This will improve our near-term algorithms. It'll let us explore even larger systems and more complicated circuits. But even at that error rate, we can't run very large algorithms or very deep circuits. And what we'll need to do at that point is implement some kind of quantum error correction. And so, so the next part of my talk, I'm going to review some of the ideas of quantum error correction. And I'm going to start kind of at the beginning. And I'm going to follow the path discovered by Shor in the mid and late 90s. Okay? I intend, please interrupt if you have questions. I'll begin with one of the simplest quantum codes. It's a quantum repetition code. And this is the encoding function. So you take this pure state and you encode each of the labels in a classical repetition code. All right, and now I will emphasize, right, we heard about the no cloning theorem. We can't copy quantum states, okay? What we're doing is we're encoding each of these basis states and we're taking this superposition to some entangled state, okay? So this really is a quantum code. It's not going to be a very powerful quantum code, but it is a quantum error correcting code. All right, this is an example where let's pick as our input state this one. So I picked an alpha and I picked a beta. And I can encode that by taking a qubit, applying that single qubit gate, and then doing 2 CNOTs. This is a very concrete example. This outputs the encoded version of this state. Right? We could build the circuit in Qiskit, we could run it, we could ask for the state, and we could plot it. Right? This is a plot of the density matrix. And you can see each of these 4 peaks. The diagonal is maybe the easiest to understand. This is the probability that you would see 0, 0, 0, and this is the probability that you'd see 1, 1, 1 with the appropriate probabilities, right? Okay, so how do we correct a bit flip error in this case? All right, the idea is really simple. We would compute the parity of the neighboring qubits, so 1, 2, and 2, 3. And what's nice is each of these states, say I flip the third qubit, then both of these branches of the superposition have the same error. And when I compute the parity check, I see a 0 and a 1 on each of these branches, right? And so this error syndrome tells me what error correction to apply. And then, of course, I can decide what to do. I can either say if I see any error, I'll just throw it out and start over, or I can say I'll look up this error correction and I'll apply it to restore the state. How do you do that? I mean, in this example, it's very straightforward. You would compute using CNOT gates the parity of qubits 1 and 2 into an ancilla, and the parity of qubits 2 and 3 into another ancilla, and then measure them. And now you have the syndrome and the output state that you would correct. Okay. Now, this seems like this is a very, very simple example, but the code can do more than just correct bit flips, and this is really kind of, it's kind of amazing. You have this state sidebar, and it encodes an arbitrary state. Okay, apparently I make the substitution here of alpha and beta. Oh, no, pardon me. So you have the state, and you apply now just a rotation. So instead of flipping the bit all the way, you partially rotate it. Okay, so here by an angle pi/4 on the third qubit. And what you get is a state that has a superposition of, it's in a superposition of having an error and having no error. And when we do these parity checks, we can measure 2 possible syndromes now. We can measure 0, 0, which occurs with probability 1/2, or we can measure 0, 1, which occurs with probability 1/2. Okay, and after we observe this syndrome, the state is now projected onto either this branch with a discrete x3 error or this branch with no error. And then we can look up the syndrome and apply the correction. So here's what that looks like, right? You can construct the circuit and you can simulate it again with the QASM simulator to look at shots. Here is the encoder. Here is the X rotation on the top qubit, and then the parity check, and then we measure the parity. Depending on the outcome, we look up a correction in the table and apply the bit flips to restore the state. Okay, and indeed, after we apply this correction, the state of these 3 wires is restored to the original state without any errors. Okay, and we can see that. So we can verify that at least in part by just measuring that register. And here's what we see. So this piece is the syndrome, and this piece is the logical qubit. And so you can see that we've already used the syndrome to do the error correction, so we can really ignore that. We can take this peak and sum it with this peak, and this peak and sum it with this peak. And we see that these occur with the appropriate probabilities, right? Okay, so we really have corrected this rotation error. All right, so just a quick summary, right? We are not copying states. We can't from the no cloning theorem. Instead, we're doing something more subtle. We're encoding superpositions into these entangled states. And then we can observe the errors by measuring a parity check. And this collapses onto, it digitizes the errors, but we learn nothing about the encoded state. And then the entropy that has been built up here from the noise gets moved into these syndrome bits. Okay, so that's the rough idea. The quantum codes themselves, right, in general, they're just subspaces of this whole n-qubit space. All right, so that's good. We can correct bit flip errors, but there's a problem with this simple example. It only really corrects linear combinations of no error and bit flip error. if we have a phase flip error, say a rotation about the z-axis, which could flip the sign of this, the relative phase of this state, we can't correct that, right? If I apply a z on qubit 1, it changes the sign here, but this is a logical error. I've changed beta. Okay, so I can't correct that. I can't even detect it. It doesn't change the parity checks. And you can see that right here. So I'm going to apply a z error here. And what's going to happen, I'll run through, I'll do the error correction, and then I'm going to read out, the only tricky part of this example is I'm going to read out in the x basis. So I'm going to do Hadamard's before the measurement. Okay? And what you're going to see is that I don't see this error. All the syndromes are 0. Okay? And the how do I read this histogram? Well, when I measure in the x basis, I apply the Hadamard gate. I rotate to this basis of plus and minus with these amplitudes. And when I encode in the repetition code, I map this observable x into this. So what I should do is I should read off the parity of these bit strings. So even parity bit strings like 000 and 011 should be grouped together, and odd parity should be grouped together. And you'll see that, for example, these peaks up to shot noise coincide with the correct value. Okay? All right, so the phase errors are a problem for the repetition code. The solution, which is what is in Shor's paper from '95, is to consider a phase flip code. Okay, so this is entirely analogous to the repetition code, but now we're doing this in the plus minus basis. Okay, so we encode now by taking a plus state to plus 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 and a minus state to minus minus minus. This is what the encoder looks like now. You can see that I've inserted Hadamard gates and I've changed the directions of the C-naughts, kind of using this identity. Likewise, to measure the parity check in this other basis, you conjugate this by the original parity check circuit by Hadamard's, and you end up with, again, now you're preparing ancillas in the plus state, and your C-naughts are going the other way. Okay? And just as an example, you can run the same kind of thing. You run the encoder, and you look at the output density matrix. Now you see it's very dense, right? We have every bit string occurring in this encoding, and this is what the state looks like. You have different amplitudes for the even and odd parts, just like I said earlier. Okay, so this code should correct phase flip errors, but how do we correct a more general error? How do we correct any error on one qubit? Well, this is Shor's code, and it's built from these two classical repetition codes. Right, so this encoder here, right, you begin with the bare qubit. First, you encode it into the outer phase flip code, and then you encode each of those wires into the inner quantum repetition code. And now, you can look at the output of this thing. It's of this form, right? So you can see that it has, if I go up here, all right. It's not totally clear. It's the same form as this in that it has the probabilities distributed on the even and odd parity strings, and each of those strings is encoded in a repetition code, right? Okay, and an amazing fact, just like the bit flip code could correct linear combinations of I and X errors, so X rotations, this code, because it can correct both bit and phase flip errors, it can also correct a bit flip and a phase flip error, and it can correct any linear combination of those. And in fact, any error can be written as a linear combination of these errors on one qubit. Okay, so this should correct a general error. Right? So let me show you that that's actually the case. Let's consider the type of noise that would occur in decoherence. So these are the T1 events that people talk about. We're going to mock up an amplitude damping channel on one qubit and show that the Shor code corrects it. Okay, so this is, I don't know if you're familiar with this, but this is a map that takes an input state rho to some output state. You evaluate this expression, and there are these two operators, A0 and A1, that describe this operation. In pictures, what it's doing is it pushes all the states on the block sphere closer to 0. It just compresses this ball toward the North Pole. Okay, and so the A1 operator corresponds to an event where you jump from 1 to 0 at some rate. And you can take this and rewrite it as a linear combination of I and Y errors. So bit flip and bit phase flip errors. This is the no jump event error. But in this case, there is a small Z component that comes along with this as well. And just because it might matter, well, it will matter later to understand the results, these are coming in at a rate root gamma. And if you expand this piece, it's order gamma. So this Z is weaker than the X and Y down here. All right. So how can I this was a super operator here. How do I implement that in Qiskit? Here's one way to do it. So you could model this damping channel as a system qubit coupled to an environment qubit. And we'll just explicitly create that environment qubit and write down the interaction that couples them. And the interaction that we want, which comes from these lecture notes and textbooks if you like, does nothing if the system is in the ground state. And if the system is in the excited state, it rotates the excitation from the system to the environment. Okay? So what we can do is we can write down this matrix for this gate, fill in missing columns so it's unitary, and then call this helper function in Qiskit, which does this K decomposition that Ali talked about earlier. And with some code here, it will build the quantum circuit corresponding to this unitary. Right? So here it is. It has 3 C0 gates and some single qubit gates. And the idea is now that if I want to simulate a damping channel, I pass an input qubit Q0 in, I put the environment in state 0, and then do the circuit, and then I throw away the environment. And if I average over all the things that happen to this environment qubit, I get a damping channel on Q0. Okay, so let's correct this damping error with Shor's code. Here's the encoder for this fixed state. This piece between these two barriers is this damping channel with rate 1/4 on Q0. Down here, I'm using A0 as the environment, and I'm going to throw it away here. Okay. Then I do syndrome measurement. So this is the encoded parity check in the plus basis. Right. So now normally it would be a parity check on 2 bits, but because of the inner code, it's on 6. Right. And then these are the parity checks for the inner repetition code. Okay, and then that's followed by taking the syndrome on each of the inner codes out here and correcting bit flips, and on the outer code and correcting phase flips. Okay. And this is the result you get if you run this. So what you see is you see a lot of bit strings, and I've color coded them to help make sense out of this. This piece down here, these 4 pairs of zeros, that's the syndrome. Okay, so when the syndrome is all 0, I have no error. Okay, and indeed, I see the same bit strings I saw earlier from the ideal encoder with the same probabilities, right? This kind of even-odd behavior. Okay. This syndrome corresponds to a Z error. It's been detected by the outer code and then corrected. You can't see it here, but probably because I don't have enough shots, but you would expect the same pattern of evens and odds with the same ratios of probabilities. And then this is an X and a Y error. So you can see this is the inner code on this block detected an error. And here the inner code on this block and the outer code detected an error. So we have both a bit flip and a phase flip error. And you can see the same even-odd behavior persists. So if we, after doing this error correction, if we just throw away the syndrome and we look at the results, right, the distribution is up to shot noise, it's the same, right? Okay. All right, so yeah, let me just say a few words, right? So you can see that error correction can correct general errors, and I've kind of gone through it in a lot of detail. But the examples I've shown you they won't work on a real device. They won't suppress error in the way that you might initially expect, because errors during the encoding operations or during the parity checks also lead to failures. So for example, in the encoding circuit for Shor's code, if I have an error on this qubit, then these gates will spread that error, and this turns out to flip the logical state of the qubit, and I wouldn't even be able to see that, right? And this is a problem in general with all these encoding circuits. I can do anything here. If I do this gate U3 wrong, then I encode the wrong state. Okay? And over here, right, if I have, for example, a failure on this parity check, that propagates up here, which is also a logical error. Okay? All right. So in addition to having an error correcting code and being able to correct errors, it's really important to limit the spread of errors due to faulty operations. And so I'm going to try to do an example where I show you how you can take each of the elements in a target circuit and replace it in such a way that the total behavior is fault tolerant. So errors are suppressed to a higher order in the physical error rate. Say if your physical error rate is p, it's going to be suppressed to order p squared in this example. Okay, so here's how you might do that. Instead of looking at the Shor's code, which is on 9 qubits, I need to sort of trim this down so that I can make a simpler example. And instead, I'm just going to concatenate error detecting codes to make a 4-qubit code. So here, the outer code is just it's just a 2-bit code now, and then the inner code is a 2-bit code. All right. So again, the checks that I need to do are parity checks on the top 2 qubits and the bottom 2 qubits, and a parity check on all 4 qubits coming from this outer code. Okay? Just so that, I mean, maybe you've seen this before and maybe you haven't, but if you see it in papers, right, there's this notation where people write a triple of numbers between brackets to describe a particular code. This means that we're encoding 1 logical qubit into 4 physical qubits, and we need at a minimum 2 errors to cause something to do an operation that we can't detect. Okay? So to change the logical state. Also, I mean, while we're looking at this picture, an easy way to see what parity checks we need to measure can come from this. We look at a particular state, say this 0 state. We know that it's an eigenstate of z. And so then we can use these relations to propagate that operator forwards through the circuit. And so in this case, this eigenstate of 0 becomes z1, z2, which is one of our check operators. Likewise, right, this eigenstate z3 of this qubit becomes x, and then a pair of x's, and then 4 x's, right? Those are our parity checks. Okay, so I'm going to go through 4 different operations and then build a circuit out of them to show you how you might make a fault-tolerant circuit. So first, I'm going to take the encoder that we had before, and I'm going to fix the state that I prepare, because we already said that if I have the freedom to put in any state I want, it can't be fault tolerant, because if I do that wrong, then that error propagates everywhere. So I'm going to fix the input state, and then just observe that this gate doesn't do anything when it acts on plus, so we can remove it. And so we end up with this circuit. And now so this circuit prepares this state. And you can observe that if I have one error that occurs somewhere in this circuit, like say I have a bit flip here, it propagates through the circuit to a single bit flip, okay, which I can detect later. You might worry about pairs of errors being undetectable. But in this case, so for example, if this gate fails and it introduces a pair of x's here, maybe that's bad. Well, it turns out that this state is an eigenstate of xx, right? If I apply xx, I just swap these 2 branches and nothing happens. Okay? So in fact, you can go and you can check, and all the ways that the gates can fail and leave errors on their outputs all are either detectable or non-errors. Okay? I need 2 independent faults to occur in order to prepare the incorrect state. For example, I need to flip the 1st and 3rd qubit if I want to flip the sign here. Okay? All right. The whole time I've been I will implicitly use a model where the gates fail independently. And when a gate fails, it introduces random errors on its output. This is a proxy for what really happens, but as I explained, it's not exactly what happens in the experiment. And you probably would have to tailor these kinds of things to your device. All right, likewise, if we want to prepare a 0 fault tolerantly, we need to use an extra trick. We put in a 0 here, and we observe now that we just have this cascade of, we're taking the 0 plus 1 state here, and we're pseudo-copying the 1 to all these other bits. So I'll just rewrite it like this. But now we have a problem because, say this gate fails, and it introduces a pair of bit flips here. Well, without any further operations, this pair of bit flips flips the logical state of the qubit. And that would be bad. It's an undetectable error. With probability p, the whole circuit would be incorrect. So we need to somehow detect this error, and discard the state if that occurs and try again. And so one way it turns out you can do that is by introducing an ancilla qubit and doing a pair of gates down to that. And now if you go through and check, all the pairs of errors that can occur in this circuit that lead to logical errors are now detectable. And they result in a measurement of 1 here, which when you see, you restart the whole protocol until this measurement's 0. Okay? So that's a fault-tolerant preparation of 0. Now we want to interact qubits that are, I'll give you, we're going to prepare a Bell state fault-tolerantly. That's going to be the goal. So we need to interact the plus and the 0. Right? It turns out that one fault-tolerant way you can do this, and it's a really general principle, is to do bitwise operations either on a block or between blocks. And so one of the most common bitwise operations that people discuss is a transversal C0 gate. So here I'm using block 1 as the control block and block 2 as the target block, and going from bit 0 here to bit 0 here, and so on. Okay, so two things to ask. Why is this a C0 gate on the encoded state? Well, you can look at how it acts on the basis states 0 and 1. Right? So if I use a 0 state as the control, then I either don't do any of the NOT operations or I do them all. Okay? But now you can see that if I XOR, if I flip every bit in either of these states, they're unchanged. Okay? So when the control is 0, nothing happens. Right? When the control is 1, instead, I will propagate 2 bit flips down to the target block, either the last 2 or the first 2. And so you can see that that flips you from between 0 and 1, right? So this is a C0 gate. Why is it fault tolerant? Well, if a single C0 gate fails, it can leave at most 1 error in each block, which we can detect. Okay, that's the main idea. Also, if the input blocks, if an input block deviates by 1 error, then we propagate that to at most 1 qubit of the other block. Okay. All right. And finally, how do we do a fault-tolerant measurement? And this turns out to be a little bit easier. In this case, we can actually just measure each qubit, and we know that first of all, we know that the measurement outcomes themselves should be a code word of the classical code. So they should satisfy the parity checks of the repetition codes that we're using. Right? So we can check the measurement outcomes, and if they fail those parity checks, we just throw it out. Now, if they pass the parity checks, then we know we've possibly observed a good sample, and we can look at the parity of bits 1 and 3 to tell us which state we're in. In this case, the parity is even, and in this case, the parity is odd. Okay, so that's a fault-tolerant measurement. All right, so let's put this together. Let me see how I'm doing for time. Okay. All right, so we'll begin with a Bell state. Hadamard, C0, 2 measurements. Okay, this is the ideal distribution. Now we want to do this fault-tolerantly, replace each of these operations by their corresponding gadgets. So here's the plus state, here's the 0 state, transversal C0, transversal measurement. Normally, we would have to do some kind of error correction or detection after this C0 gate, but because this measurement itself is somehow doing error detection, we can push that through and remove the error detections from the circuit, okay, which makes it simpler, which also makes it more reliable. Okay. This is the histogram of the fault-tolerant circuit when it's run ideally. Okay. This bit here is the flag that's telling us that we successfully prepared 0, this block. And the rest, those are combinations of code words from the 2 4-bit codes. Okay. So we can set up a simulation with noise using error in QuizKit. We can define a noise model. So this is how you would define a depolarizing noise model. You give the channel and the corresponding probabilities for each of these types of poly errors. You define a readout error, and then you attach them to operations and return the model. Okay, so then we make a noise model with roughly a 1% error on everything. And we can run this on the QASM simulator, pass this noise model in, and ask for a lot of shots and then run it. And so what do we see when we run this fault-tolerant circuit? I think the slides will be available later, so we can come back to this. Okay, so here's what we see. On the left is what we get if we run this circuit bare without any encoding. And so you see you get, these two, well, okay. Yeah, so these two peaks are roughly equal, and that's our Bell state, 0, 0, and 1, 1. These are errors. These are failures. And so those are occurring at around the 1% level, which is what we'd expect from the noise model. Okay? If we run it through the fault-tolerant circuit, here's what we see. All right, we see a lot more outcomes. All right. Some of these outcomes, this top bit is 1. These are the ones where we failed to prepare the 0 state. So we should just throw it out and try again. Okay, so we discard all those. These others, all these other green bars, are cases where the code word doesn't satisfy the Z parity checks. So we throw those out too. We know they're failures. And the rest are successful runs. We would accept them into our histogram, or we'd accept the output as being correct. And you can see that in all these cases, right, you have 0, 0, you have 1, 1. And in fact, the distribution is close to what you'd expect if you sum up the probabilities in all these bins. Okay? So just to show you what happens then, if you vary the physical error rate that goes into the simulation on this axis, and you look at the probability of observing a sample that's incorrect, like logically incorrect, without encoding, you expect it to go to be order p, right? And it is. Okay, with encoding, right, there's some probability that you throw out the result because it failed some error detection in the middle. And so that happens again with order p. And in fact, it's pretty close to the number of gates in your circuit times p. But if you accept the state because it passed all the error detections, the probability that you fail now goes like p squared, which is exactly what you want. And that means that at some error rate, which is actually above 2% in this example, your probability of failure, so of thinking that of passing all your checks and still getting the wrong answer, is much lower than your physical error. Right? So here this is order 10 to the minus 3 from a physical error that's order 1%. Okay? So that's the idea of quantum error correction illustrated within error detecting code and the idea of fault tolerance. Now I think I have very little time to go through the last quarter. So what I'll do is I'll just give you a very quick idea of how you apply these more generally. Okay. There are many other kinds of error correcting codes. One of the leading examples that people talk about is a surface code. Here, the check operators are defined by a tiling of a surface, and the surface has some holes or handles or something that tell you how many logical qubits are encoded. Okay. A kind of code that people are interested in is called a rotated surface code. It's just an example of one of these surface codes. And errors end up looking like strings on these surfaces, and the syndrome shows you the end of these strings. And that's how you can detect and correct the errors. And here you can actually correct the errors. You can do more than just detect them like in the other examples. You can compute syndromes in a similar way by computing parity checks. And there are ways to initialize and measure the qubits. The way you would do some kind of error correction is you'd repeatedly measure the check operators. Over and over again, you gather these planes of syndromes, and these all go to a classical processor where you make some inference about what happened and update your belief about the current state of the system. There's a decoding problem you have to solve to do this. Solving it optimally is hard, but there are some algorithms that do efficiently find the most likely error. This is a sketch of what it looks like. You get these syndrome planes. You see the endpoints of these error chains, but you don't know what they are. And you go through some processing steps to pair them up using something called minimum weight. It's a minimum weight matching problem. And you commit to some of the corrections. You apply the corrections, and you move forward. Okay. You can simulate large error correction circuits with stabilizer simulations using the Gottesman-Canil theorem. You can propagate errors through Clifford gates to update the errors in the future. So as faults occur, you can update what you think the error is. And you can then pass these to that classical decoder, and you can make predictions about what will happen for a poly noise channel when you use a quantum code. Right? So you can see your physical error rate and your logical error rate, and you can look at how that behaves, and you can you can make some prediction about the error rate. In the case of the surface code, the rotated one that I just showed you, you can look at patches of increasing size. So this size, 357, that's the number of qubits on the edge of the square. And as you increase that size, you're also increasing the distance, the number of errors the code can correct. And what you see is that as long as you're below some threshold error rate, so here this is a C0 error rate of about 0.67%, going to larger codes actually reduces the error, which is exactly what you want. And in principle, you can make this as low as you'd like by increasing the size of this as needed. Since I'm nearly out of time, the important point is that the threshold here it's a constant. It doesn't depend on the algorithm you're running. It's just a function of the noise model and the quantum code that you're using. But then you use these ingredients and you make these replacements, these fault-tolerant replacements in whatever algorithm. Your threshold is still the same, whether you're doing algorithm A or B or C. In the case of the surface code, something kind of wonderful happens. There are ways of doing gate operations fault-tolerantly in such a way that the threshold is unchanged. Okay, so in the last 30 seconds, there's a lot more to quantum error correction. If you're interested, there are a lot of ideas that are still being explored, and there are a lot of relatively recent discoveries. I just made a few slides with some of these. There's an idea called gauge fixing, which is a wonderful way to do universal computing or to make more error resilient codes, a way of understanding fault-tolerant gates and surface codes. There are higher rate codes that encode many qubits into a block. These have the potential to be very efficient. They go by the name of hyperbolic codes or hypergraph product codes. There are really a variety of great ideas to be interested in and to explore under the name of subsystem codes. These are codes that have a property that make their parity checks easier to measure. Magic state distillation is a way of getting a universal gate set if you have a system where you already know how to implement fault-tolerant Clifford operations. And there are new ideas for how to build these fault-tolerant gadgets using something called flag qubits. Finally, there are more recently people have been exploring continuous variable error correcting codes, encoding qubits into oscillator modes and things like that. These are called cat and binomial or GKP codes. And there are even ideas for concatenating those codes with sort of more standard codes to build reliable systems. All right, so thank you. Reviewed the quantum computing devices, transmons. We looked at quantum volume. We looked at some basic error correction experiments and explored those a bit with QuizKit. And we looked at some of the basic ideas of fault tolerance. So thank you. If you have any questions.